Hi, and welcome to this tutorial. In this video, I'm going to show you how to run a confirmatory factor analysis in R. But before we do so, I quickly want to provide a very brief introduction to classical test theory. Because confirmatory factor analysis are in fact based on classical test theory, so it makes a lot of sense to understand at least some of its basic assumptions. So let's get right into it. Why or what is even the goal of running a confirmatory factor analysis? So in the social sciences, and therefore also in communication science, we are very often interested in somewhat abstract concepts. Think about, for example, emotions, attitudes, literacy, or personality. These concepts cannot be measured directly, unfortunately, right? But what we can do is we can assess them indirectly using observable indicators. So, for example, items in a questionnaire. So this is why we often create several items that are meant to provide some information about whatever underlying trait or disposition we want to capture. Now, test theory explains the relationship between this latent variable, think about, for example, personality traits such as extraversion, and the responses to several items that are designed to at least provide information about this latent variable. For example, an item like I make friends easily or I know how to captivate people can of course be seen as expressions of this underlying trait called extraversion. So classical test theory defines the statistical relationship between a measurement and the actual characteristics of interests. Now, in the tutorial I will use different terms, and so I want to introduce them now. Now, it is really important to understand that the basic assumption of classical test theory is that the trait explains response patterns in items. Now, if we want to investigate this relationship further, we need to differentiate the following concepts that you see here in the table. Now, first, we have to distinguish latent variables. So these are our concepts of interest, the ones that are not directly observable, and we're actually going to call them also factors later. And again, think about things such as emotions, attitudes, personality, literacy, concerns, motivations, and so on. We have to distinguish them from the manifest indicators. So these are the measurable aspects that should be influenced by this latent variable. So for example, responses to items in a questionnaire. But be careful here, it's not only or it's not always items in a questionnaire, it can be also other types of things, other ways of measuring things. Then we have to distinguish the true score, actually classical test theory is often also called true score theory, from the measurement error. So the true score, and I will explain it even more in a bit, is the share of the variance in the measurement of a manifest indicator that is directly linked to the latent variable. So this is the share of the measurement that we are actually interested in, which we want to estimate to the best of our abilities. And we can do so by removing or trying to remove the measurement error. This is the share of the measurement variance that is not linked to the latent variable. And this includes, therefore, item-specific variance. Each item is different, so naturally each measurement will be slightly different, but that's not what we're interested in. We are interested in what they have in common, what signifies or what is related to the actual latent variable that we're interested in. So it includes the item-specific variance, systematic errors, as well as random errors. Again, I will explain all of these in a second. So in classical test theory, we decompose the variance of each measurement of a manifest indicator. This means that every observable measurement, which we can denote as y, is composed of variance that is explained by the latent variable, which we also call the true score, or tau, and the variance explained by the specific manifest indicators, which is also a type of true score, and then the measurement error itself. So we can come up with the following formula here, which says again that y equals tau A plus tau B plus epsilon. The measurement error hereby is independent of the true score, and it varies randomly across persons and measurement occasions. So we can say that the correlation between the true score and the error is supposed to be 0. Now, measurement errors can be divided into two components. The first one is random error, which is indeed completely independent, and sometimes, unfortunately, also systematic error. Now, random errors are those errors in measurement that lead to measurable values being inconsistent when we, for example, repeat the measurement. Systematic errors are errors that are not determined by chance but introduced by some sort of inaccuracy. So this may involve the observation itself or the measurement process. So systematic errors can be, for example, imperfect calibrations of the instrument or some sort of interference from the environment. Think about it this way. People will answer to an intelligence test differently when they are really tired or when there is a noise distracting them from the task. This is, of course, not really the latent variable, intelligence itself, that we are interested in, but some sort of interference that may bias or change our measurement. So, whenever we aim to measure an abstract concept, we usually estimate something that we call a reflective measurement model. And the panel 1 here actually shows one in a path model. And as you can see here, we specify a latent variable eta that explains people's responses in several items, here denoted as x1, x2, and x3, while taking the item-specific error, epsilon1, epsilon2, epsilon3, into account. Now, bear in mind, we already learned that the item-specific error is composed of item-specific variance as well as measurement error. Now, in most cases, not all items are equally well explained by the latent factor. For some, for example, the true score will be lower than for others. So this is denoted by the different factor loadings, the lambdas here in this representation. You may wonder, why is there a second panel that is called formative measurement model? So there's actually also a different type of concept in classical test theory that's called a formative measurement model. Here, the combination of individual factors or indicators make up the formative factor. So think about, for example, the value of a car, which is not necessarily or does not explain in a way answer options or something like that, or response patterns. It's more or less made up of different things such as age, condition, the size of the car, what type of model it is, and so on. In this tutorial, we will actually only talk about reflective measurement models, again, in which the latent variable explains the measurement. And in this tutorial, we will estimate a reflective measurement model using confirmatory factor analysis in R, and a so-called CFA can be best estimated using the package lavaan, which I will introduce later in the tutorial. But as we will engage in some data wrangling beforehand and also run some item analysis beforehand, there's actually two packages that we will load up front, which is first of all the package collection tidyverse. We are using a couple of functions for data wrangling. But then to assess items individually, we will actually load the package psych, which provides some nice tools to assess, for example, the psychometric properties of variables. So with that said, let's start the actual tutorial. Okay, so I opened up R, I opened up an empty script, and just a disclaimer up front, I will sometimes just write the code here directly, sometimes also copy paste it from the tutorial that you just saw. So if you work with the tutorial, it should be easy to get the code, but at times I will just simply write them. So in the first step, we are going to load our packages, which is, as I said, the tidyverse and the library called psych. And now, of course, we need to get some data. And what I want to do today is work with the Big Five personality inventory. So this very classic, known psychological model that more or less argues that personality can be differentiated into 5 different dimensions. And lucky for us, it's actually a data set that measured these 5 dimensions with a couple of items is actually included in the psych package, so we can actually use that. So I'm getting some data which I will actually directly transform into a tibble, because then we can actually have a look at it in a better way. And we can actually just get the data by using the command bfi. So as you can see, when I load this, I already have a data set now with 2,800 observations and 28 variables. Let's quickly take a look at the head of this data set. As you can see, it contains a lot of variables that are already nicely named. So A1 to A5 is actually items measuring agreeableness, C1 to C5 is conscientiousness, and there, of course, accordingly, we also have 5 items for extraversion, neuroticism, and openness. There's actually quite a nice documentation page for this data set. So if we run the help function, you can see that the documentation is quite thorough, and most importantly, we can actually see the item formulations. Now, whenever we engage in factor analysis or scale analysis, it's really important to always have the item formulations by our sides, because they will tell us also how to deal with these items. And any item analysis or factor analysis is always a combination of looking at the statistical results as well as the items itself and making good theoretical choices. Now, one of the first things that I'm seeing here already is, for example, that the first item here, A1, is inversely formulated. So it's not actually measuring agreeableness, but the opposite of it. So it says here, I am indifferent to the feelings of others, but being agreeable means you're not indifferent to the feelings of others. So we actually have to recode quite a bit of the variables. I already included the code for that in the tutorial here. So we're just simply going to copy paste it into our R script. So this is now about recoding our variables. And as you can see, what I'm doing is I'm selecting all the items from this 25 item scale. It's important to note these items are measured on a 6-point scale ranging from 1 very inaccurate to 6 very accurate. And I'm using a very simple trick to actually recode all of them in one go, which is I'm just subtracting the number of answer options plus 1, so in this case 6 plus 1, from the item, and this already makes gets close to an inverse version of these items. So for example, the value 6, the answer option 6, then becomes -1, 5, -2, 4, -3, and so on. So the only thing that we then have to do is actually multiply it by -1, and it will be actually then inversed. So this bit does the inversion. I now created a new object that I called BFI items, which contain all these 25 variables, 5 per dimension. Now, in the next step, or in any confirmatory factor analysis, we should investigate our items first. We should look at some of its psychometric properties, whether it's normally distributed, and just check some assumptions that are required for any of these analyses. A very simple way to do that is normality assumption is what I want to do. And a very simple thing that we can do is use the describe function from the psych package around all these items. And this will produce actually a quite nice table with a good summary of our items. So as you can see now, all items, each item is one line, and we can see how many people have answered them. There's a couple of missings in the data set. We can see the mean, the standard deviation. We can see min and max, of course. But most importantly here now, we can have a look at skewness and kurtosis to check whether these variables are normally distributed. So if I just look at these values here, all of them are actually not that bad. We have a couple ones that have skewness values higher than or below -1. Here's another one, +1. So this means, of course, that they perhaps a little right or left skewed. Based on the skewness parameters, we should not be too concerned, but perhaps it would be good to actually look at this visually. So we can perhaps create a plot that shows us the normal distribution, or whether it's normally distributed in all of these items. And I created a little code here in the tutorial that we can use, and let's see what it actually does. So I will actually run it in one go so that we directly see the relevant plot, but then we can go through it one line by line. So as you can see, it creates histograms for all these items. We actually use faceting so that they're all in one plot, which is nice to compare also a little bit. The way that I'm doing this, I am transforming this basic data set that we had, consisting just of the items that measure apparently these 5 dimensions, by transforming it into a long format, which actually looks like this. And this actually then can be used to plot the histogram based on this value column. And the only thing that we have to add is then a facet wrap with the key variable here that contains the variable names. Of course, they're here abbreviations. And yeah, the rest is just a little bit of layout adaptation so that it looks a little bit nicer. The most important part now is we can see now that most items are fairly normally distributed, but some of them are also quite skewed. So for example, the item A4 here seems to be a little bit problematic. There's another one here at the bottom. None of them are really very bad. They all cover the entire range of the answer options, so that is a good thing. But of course, we should perhaps keep in mind that some of these items are a little bit potentially problematic. Whether they are actually problematic or not is something that we will only see later, but if we see problems with items, it could be that it's related to these particular distributions. Now, another check that we should do up front is an extension of the normality distribution check, which is the multivariate distribution check. And that can again be done with a function from the psych package, which is called MADIA. It actually conducts the MADIA test of multivariate distribution. Again, we just provide the object with our items. We're not going to do a plot in this case, so we are going to say plot equals false. And if I run this, it actually tests the assumption that there's multivariate skewness or kurtosis. We get here the relevant significance test, and in this case, all of them are significant, which means it's not multivariantly normally distributed, neither with skew or kurtosis. And this again, of course, is an assumption that is violated. It's not that problematic, but it's something that we should take into account. For example, similar to when the Lavaan test the assumption that variances are equal is violated in analysis of variance, we should use perhaps a more robust estimate or robust version of the actual analysis. So this is what we're actually going to do later on as well. So now we can actually start to estimate our confirmatory factor analysis, and for this we are going to use the package lavaan, as I said before. Now, lavaan is a very powerful package because it provides a very convenient and straightforward syntax for fitting structural equation models in general, and measurement models are technically structural equation models. So let's get into how this syntax works. First, we always need to define the latent factor that we are interested in, or in our case, actually 5 different ones. Now, for each latent variable, we use sort of the same format. We provide a name for the latent variable. Then we use a expression which is an equal sign and a tilde, which more or less says this is, or manifested by, this latent factor is manifested by, and then we just list all the items with a plus that we believe make up this latent factor. The reason why this model syntax is comparatively short is that because of behind the scenes, the function that we will later on to run around this model takes care of several things. It, for example, by default, fixes the first factor loading of the first indicator to 1, thereby fixing the scale of the latent variable. And at second, also the residual variances are added automatically. And also third, all variables are correlated by default. These defaults can be changed and can be individually customized, but for our purpose now, we can just run with the default, it's fine. We can generally now, when we actually run the model, as you can see here, this is how the syntax is specified for the particular model that we are interested in, the big five model. As you can see, I'm actually naming the latent variables meaningfully, and then I'm just saying which of the items make up each of these factors. Comparatively easy. They are wrapped with quotes, so this is actually a string, and we save the string. In this case, I call it just CFA model, a new object that contains the string. Once we have done this, we will wrap the string with a function that is called CFA, so a simple function standing for confirmatory factor analysis. The first argument is this particular string. The second argument in this case can be an estimator. By default, actually, if we don't specify it, it's maximum likelihood. But as I said before, because the MADIA test for multivariate normal distribution was significant, we may rather use a more robust version, the robust maximum likelihood estimation, which is abbreviated by MLR. And the third one, we have to, of course, provide the function, as always, with the data set that we want to estimate this model on. So let's run this particular code. I'm just going to copy paste it into R again. And this is about estimating the model. And I'm gonna make a little bit more space. So we run this entire string. So if we just have a look at this object, it's actually a string containing all of this information. We don't have to worry about that too much. But now we can actually estimate the model by running the CFA function. Now, R tells me that it cannot find this function. It's because I haven't actually loaded lavaan yet. So if I do this, it should work in the next step. Right, so this works. We simply saved our results into a new object that is called fit.cfa. Now, in order to get our results, we can do several things. And the first one that we will actually do, we will check the model fit. In order to do that, we can use a function that is called fit measures. Fit measures, and the M actually is uppercase. That's important. The first argument is simply our estimated model. And the second argument is a vector that extracts the relevant fit indices that we may be interested in. So if I run this function, I'm actually getting the different fit indices for this model. We get a chi-square. In this case, it's scaled, the robust version. We get the degrees of freedoms, the p-value, the CFI, the TLI, and the RMSEA. Now, overall speaking, there's lots and lots of fit indices. These are perhaps some of the most reported ones. And all of them have different properties, so we should look at them in combination. And the usual approach is that we look at all of these values and check whether they exceed certain thresholds. Now, the problem is that these thresholds are usually somewhat arbitrary. So perhaps let's start with the easiest one, the chi-square test. In this case, we test whether the model fits well with the data, and if it's significant, it means there's a significant difference between the model implied covariance matrix and the actual covariance matrix. So if it's significant, the model doesn't fit the data that well. The problem with this is that with comparatively large samples, and in our case we have a sample that is higher than 2000, it's very likely that it becomes significant. So even small deviations between the model implied covariance matrix and the actual covariance matrix are going to be significant. So perhaps looking whether this chi-square, and here's the p-value for it, is actually significant, in this case it is, may not be the best assessment. So this is why we look at some others, and for example the CFI and the TLI are values that range from 0 to 1, and the closer they are to 1, the better the model fits the data. And as we can see, we have here values of 0.78 and 0.76, so it's there's a certain fit. However, common thresholds suggest that only fits above 0.9 or even 0.95 should be considered good. So in our case, the model actually doesn't fit the data well. The RMSEA is sort of inverse. The closer it is to 0, the better it fits. And there's various, again, different thresholds. It should be below 0.8, which is the case here. So this particular one seems to be okay, but the CFI and TLI are actually not very good. Now, let's nonetheless look at the entire model, and we can do this by using the the summary function. And the first argument, again, is, of course, our fitted model. But we can add two things. The first one is we also want to see standardized coefficients. And the second one, let's also add the fit indices that we actually extracted individually here to the output. Now, if we run this summary, it's the same function, so it should be fit, not std. Now, if we run this, we get a very, very large output that contains a lot of information about our model. So let's have a look at it. This is actually this output consists of several parts. The first one here, all the way here, is sort of the header. It just contains the optimization method, the number of free parameters, and perhaps most importantly, how many cases were used for this analysis. In our case, 2,400 of the 2,800. And then the second part here, the model test, the test of the model, contains the chi-square that we actually already extracted earlier, and its p-value, but it also contains other indices, so the comparative fit index, CFI, TLI, that we already extracted before, robust versions of it, as well as here different other criteria that we can use to assess our model. The other one that we looked at was actually this RMSEA. Now we know already that the model doesn't fit too well, but let's actually check out the third part of this output, which shows us factor loadings for our latent variables. So as you can see, it's organized in a very nice way. We can see that agreeableness here is made up of these 5 items. And if we look to the last column here, we see the standardized loadings, factor loadings. So earlier I said these are the lambdas in our reflective measurement model. They tell us about how well these items are explained or load onto the latent variable. And as you can see, lots of them are doing quite well. They are above 0.5, which is a usual threshold a lot of scholars consider as good. But we also have a first item here that is very bad. It has only a factor loading of 0.3 and therefore is not as good. If we just cursorily look at all of them, we see that there's always, decent factor loading, sometimes a bit lower, sometimes a bit higher. Openness here seems to be a bit problematic, and that's also, of course, something that we can consider. Then we also get a table with the covariances between the latent factors. So in confirmatory factor analysis, as I said, when we specify the lavaan syntax like we did, all the latent variables are actually correlated by default, which is often a very meaningful and appropriate assumptions. So as we can see, for example, conscientiousness and agreeableness are actually correlated, not very strongly, but moderately. Here's the significance for this correlation. And we can also see that extraversion is also positively correlated with agreeableness. We can also see that neuroticism is negatively correlated with agreeableness. So this table provides us with the interfactor correlations. And below here we also get variances. I'm not going to go into depth in what all we can learn from this particular output. The most important part for us is these covariances, the factor loadings, which are not great in all cases, and overall the model fit that we looked at here. Now, given that our model didn't fit the data too well, we may want to investigate possibilities to improve our model. And one thing that we already did, or that we already could have done, is we looked at, and let me actually open up it again, so the summary here. And we looked at the factor loadings, right? And we could, for example, decide that this first one here doesn't load well onto the factor, so we may want to delete that one. That's actually a pretty good choice here, actually. But we can investigate the model further and find out perhaps different ways to improve the model fit. And we can do this by extracting so-called modification indices. And this can be done with a function called mod indices. And it just takes our fitted model again, and because it produces a quite big data set, I'm going to arrange it directly according to the major column, which is called MI, and I will do it in a descending order, and you will see in a second why. So this creates the following table here, and this is a quite interesting table because it tells us in a systematic way how we can improve our model. And the most important column is this one here, the MI column. Because it tells us how much we can reduce the chi-square if we do whatever it's suggesting us here. Now, of course, we have to learn how we can read this. But a word of caution, just optimizing based on all of this is a very, statistical approach to model improvement. We should always also check whether this aligns with our theoretical thinking. It is therefore often useful to have our item formulations open here as well to try to understand what we are actually doing here. So in the biggest improvement could be made if we account for shared variance between the items N1 and N2. So let's open up N1 and N2, and you can see I get angry very easily and I get irritated easily. So as you can tell, they're very similar items, and they're actually quite different than, for example, I have frequent mood swings or I often feel blue, right? So the model recognizes that these two items might have some common variance that we should account for. So one way of doing this would actually create a sub-factor within neuroticism that actually only contains these two items, which is perhaps not the best idea because we want to keep the big five structure, the five dimensions. So, but what we could do, for example, is remove one of them, because then the model won't see that they have this common shared variance. The second line here tells us that the fourth one, which is I often feel blue, actually has cross loadings on the factor extroversion, which it should at best not belong to. So again, extroversion is I find it difficult to approach others. I know how to captivate people. Again, some are inversed. I don't talk a lot. I often feel blue. Yeah, you can see how that relates to one another. So this is perhaps not a very good item that we could also, again, consider removing. And as you can see in this way, this table suggests quite a bit of possibilities to improve our model. I won't go into depth into what we can do now. It should be a good balance between trying to understand the items and why the model or the modification indices suggest these particular improvement. In the tutorial here, I already included some potential improvements. As you can see here, I'm changing the syntax only in slight ways. I'm removing A1, I'm removing N2, and I'm removing O4. And the basic idea is that we just rerun the model with these adjustments and check whether model fit increases and whether the entire model still makes a lot of sense. So I'm actually just going to copy paste this here. So I'm removing some items. I'm actually saving this in a new object to just not mess with my old model. I'm estimating it again, and let's have a look at the outcome. Now, as we can see, the outcome looks very similar. Let's first check the model fit itself. So the first thing that we can see is that the chi-square value actually has been reduced. So it's smaller than it was before. I think before it was above 3,000. But it's still significant. And as we can see, the CFI and TLI are still not great. It did improve, but not to levels on which we can consider this an acceptable fit. But overall, we can now see that all the factor loadings are above 0.5, so that is a good sign. There's still possibilities to improve the model. It's still not great. For now, I just like to stop here and think about some more steps that you usually need to do in confirmatory factor analysis. But based on this model, we have to conclude that it does not fit the data well yet. So based on the data set that we have, we would conclude that the 5-factor solution is not the best for these particular items. Perhaps even though our theory suggested that way, and the items were even designed with these dimensions in mind, it still doesn't fit the data well. Now, another aspect that we should always look at, particularly once we have established a good model fit, is reliability. So the additive variance decomposition that we already used to estimate our latent measurement model is also the basis for one of the most important estimates in classical test theory, and that is the reliability. Now it can be defined as the share of the true score of the measured variance. So in other words, the variance of tau divided by the variance of the entire measurement, y. And of course, the entire measurement is nothing but the variance of the true score and the variance of the measurement error. Now, if we have a multi-item measure, and we usually do, and in our case we do, the covariance between any two items of the same scale represents the true score. The correlation is what sort of makes up whatever we are interested in here. Now, in practice, there are several different scores that we can look at. One of the most common ones is Cronbach's alpha, of course, but this is perhaps a little bit problematic about Cronbach's alpha. It assumes tau equivalency. So in other words, that all the factor loadings are the same, which, as we already saw in our model, is not the case. And in fact, it's actually it's almost never the case. So alternatively, we can also look at, for example, McDonald's omega, which is also known as composite reliability. And conveniently, there's a package called SEMtools, which provides some functions to extend the functionality of lavaan. And one of the functions that we can use here is called simply reliability, and it computes all the relevant reliability estimates. So let's have a look at that as well. And because I'm only going to use the function reliability, I'm going to put the package just in front of it with 2 columns instead of actually loading it. And as you can see here, we get a nice table that summarizes the reliability for all of the 5 dimensions. We get in the first line or the first row Chromebus alpha, and as you can see, it's comparatively good for almost all dimensions. As you may know, that Chromebus alpha is deemed acceptable if it's above 0.7. It's not great, but it's acceptable. Here, openness is not very good, so here we do have a little bit of a problem. The omega 3 actually is the McDonald's omega, which I mentioned before. So in our case here, it doesn't differ that much from from Chromebus alpha. This is because the factor loadings are comparatively similar. They don't differ that much. But for example, in the last dimension, you can actually see that it's even lower. So there's a problem as well. We also get the average variance extracted, which is another interesting value to take into account. So this is how much on average the latent factor explains in these items, and of course it should at least be somewhere around 50% or more. So as you can see, all of them are below 50%, so that's also not that great. Again, this aligns with the model fit, which is not great. Our reliability assessment is equally not that great. Now, before we end this tutorial, I want to ask the question, so why are we even bothering about this? You may have seen lots of papers who simply report Chromebus alpha, and in our case, actually, if you would have reported Chromebus alpha, it would not have been, it wouldn't even look that bad. But I'd like to use a citation from Bolland from 1989 here, and says, if we ignore measurement error, it generally leads to inconsistent estimators and thereby to inaccurate assessments of relations between the underlying latent variables. Now think about, for example, the relationship between intelligence and academic performance. Now if we estimate this based on just mean scores, something that is very often done, the relationship will be lower than if we actually look at the correlation between the latent variable that we estimate based on a confirmatory factor analysis. So as this figure shows, if we estimate intelligence, and in this case academic performance, based on these manifest indicators using structure equation modeling and the CFA that we did, we can also estimate the correlation between the two. And it will usually become bigger or larger, right? Because we parcel out measurement error. In other words, we make the measurement more precise. And if we make the measurement more precise, we also gain higher precision in estimating a relationship between two variables. Now we can check this in our example with the following code. So why bother? And what I'm going to do is the following. I'm first going to create the mean scores for all of these 5 dimensions. And as you can see, I'm simply doing it mathematically. And in the first step, I'm actually going to produce the correlation between, in this case, agreeableness and extraversion. Right, so I'm using the core function to produce the Pearson's correlation between these 2 mean indices, and I'm actually saving this in core 1. And if you have a look at it, the correlation between these 2 latent factors is 0.5 based on the mean scores. Now we can use a function that is called parameter estimates to extract these latent correlations from our original model, from this model that we have estimated earlier. Right, so if I use here parameter estimates, I get an outcome table where all of the estimated parameters from our model are included. And as you can see, it actually also includes the correlation here, for example, between agreeableness and extraversion. Now we can already see it here. It's actually 0.69. It's already much higher than the mean correlation. Now I actually want to only get this particular variable out of this, so I filter based on these 2 values. So the left-hand side should be agreeableness, the right-hand side should be extraversion, and I'm only selecting this particular column, which is the column std all. So, and I'm also transferring it into a numeric value. If I do this, as you can see, I'm only getting this one value. I'm actually, again, going to save it into an object and just bind them together so that we can see them next to each other. So what do we see here? We see on the left side the correlation between agreeableness and extraversion based on mean scores, and then based on the true score that was estimated from our confirmatory factor analysis. And as you can see, it's much larger. This is because we increase the precision with which we measure both agreeableness and extroversion. And this should show already quite vividly that, accounting for measurement error in our models is good because it, heightens the chance to actually find meaningful effects. Now think about that. A lot of communication science effects are really, really small. And because they are small, we probably should take care to reduce the measurement error in order to actually be able to find them. Yeah, this was just the end of this tutorial. There's a lot of resources that you can check out in order to learn more about test theory and confirmatory factor analysis. Of course, this was a very short and brief tutorial. There's a lot more ways in how you can specify measurement models, and a lot more discussion about what is good practice and bad practice. But I hope this first tutorial gave you some idea about how to run this in R, and particularly with lavaan. So thanks a lot for listening, and try it out yourself using the tutorial that I created.